try to connect these two converters together to be something like boost buck converter cascaded, removing this load and this input and connect the output of the boost converter to the input of the buck converter. We'll come up with this converter. So here we have the two converters connected to each other. This is simply a boost cascaded with a buck converter. So we can say that this is not the choke converter. It is a boost buck converter. It has two advantages. One of the advantages is that the input has an inductor, which means we have a smooth and continuous conduction at the input, and also the output is connected to an inductor, which means also we have a smooth energy transition in the output, which is not the case for the buck and the boost converter. Yes, the boost converter has smooth transition for the energy because the input has an inductor, but the output, the load side, it's pulsating. If you consider the load, the capacitor plus the resistor, the current that's coming to this side to be pulsating, and the problem is more complicated for the buck converter because the pulsating current coming from the input directly, which means we have to add some maybe storage devices. If you look at this boost buck converter, we already have
this side is boost, this side is
so we have smooth transition for the energy for this converter. But also we have another problem, which is that we duplicated the number of switches. Here we have two switches, and also here we have two switches. What we can do actually is to operate these two transistors together, so we can simply replace them with one switch, and by default these two diodes will be operating together. We can take this inductor to this side, no problems. It's in series with this load, so we can replace them, that's fine. And we can also change reflect this capacitor, so we can find that the choke converter circuit can be simplified as follows. Since we reverse this output, so this will be a negative output, because you find now that the current is flowing in the opposite direction. So here we have a capacitor, inductor and we have a voltage source, and this switch can be replaced with only one switch. When this is conducting, this will be open circuit. When this is conducting, then the other side will be open circuit. So this switch is moving from here to here. And this is the interesting part in the choke converter. The energy transition between the input and the output is achieved by using a coupling capacitor, not the inductors only. So the capacitor plays an important role here by transferring the energy from the input to the output. You see how we know that the current average inside the capacitor is equal to 0. We'll see now how
the current should be
special converters.
For capacitor, the average voltage is constant. So the average current is 0.
Is a short circuit, and the current will be flowing in this direction. And this inductor will start
charge the inductor.
All devices here are charged.
So you will charge
the inductor. And also at this moment,
and also this way,
current
charge
the
inductor. So this inductor and
this capacitor is charged and it has voltage at this moment.
This on.
This switch is
This loop.
Because
this loop together
to 0, for example. So the voltage across this diode will be in the reverse bias. We make this diode be off. So this
so they go here. So this is off.
Also will be flowing.
It's off. It's off.
So here we have two.
So we have a loop here.
Number one, the
we have another loop
direction. At the same time, the current is also flowing in this direction. And here, the current inside this transistor actually combines both the input current and the output current. The current that's
we have two current loops.
This inductor
Input
and the current that's coming from this inductor. Now, when the switch is off, when the switch is off, what happens? So this will be open circuit.
Then this on.
Here. So there's no current coming in this side. What happens
So
is
this
that
open.
this diode will
This
be
on.
in the forward biased, because now this short circuit here, or this voltage that was applied in the reversed direction is released, so the current will flow in this direction, and the current
And we have
also will
a current
flow
here.
in this direction.
This way.
So here we have two currents.
And
the
this
switch is
way.
on, there is current flowing
You see
like
this
this,
current and this current.
when the switch is off, we have current flow
Two current.
like this,
One
and
is here.
so that's what's
Another is
happening
here.
inside the choke converter. The
So this is
thing
choke
here,
converter.
for this capacitor, for this coupling capacitor, when the switch is conducting, the current on this capacitor will be the same as the current that's coming from inductor L2, will be this current. And when the switch is off, so the current will be, the current on this capacitor will be the current that is coming from this side, to be L1. So when the switch is on, the current IC will be how much? Will be the current of L2. When the switch is
So if
off,
this
the
off,
current will be IL1.
This
So
is
here we
equal
have
to
two currents
IL2.
inside this
If this
capacitor,
off,
and the average of
this
these
is
two
equal to
currents will be
IL1.
zero, but there is no problem, because each one of these currents come into this capacitor at different cycle when the switch is on and when the switch is off. And that's how the capacitor, the coupling capacitor here, transfers the energy inside the choke converter, not the inductor. Let's try to find the average voltage across the coupling capacitor here and see how much the voltage across this capacitor will be. So if you try to find this voltage using the outer loop here, the average voltage on these inductors should be zero, because we expect that we are operating in a balanced condition or in a steady state. So we can say that minus V input plus VC1, the average across this capacitor, minus the output is equal to zero. So VC1, the voltage across this capacitor, is equal to V out plus Vin. So this capacitor must be able to tolerate the value of the input voltage plus the value of the output voltage. And when the switch is conducting,
VC1 is large, then
so the
V1.
current will be flowing in this direction and will be flowing in this direction. And if we try to draw the current,
So you can see VC1 is V1 plus V1. This one plus this one.
Which is conducting, and the slope here will be how
So
much?
if this turn on,
input over
the inductor current
this
increase.
time 0 to delta Ts. Now when the switch is off, what happens at this moment? The current will be flowing in this direction.
So
and
then
also
flow in this
flow in
direction.
direction through this diode. And the voltage, of course, will be in the opposite
So
side.
pick one,
where the current is
assignment.
reversed. And here, the current inside this inductor will be released because
This
it
turn on,
will
increase.
charge the capacitor at this moment. So you find that the current here will be something like this.
Increase.
And the slope at this moment is equal to how
If
much?
this turn
V
on,
input
go this way,
minus
because
V
this voltage is
C1
very huge.
over L.
And
Now
inductor
VC1 is equal
current
to V out plus Vn, right? From this equation, this is the voltage on the capacitor. When we say
V1 minus VC1 divided by L. VC1 is large than V1, so this become negative.
Input will go with this. So here we'll end up with minus V output over L.
And then we can obtain minus V out plus minus V out.
In this inductor to find the relation between the input voltage and the output voltage. So we can simply say this slope, which is Vn over L, times delta Ts is equal to minus V out over L, which is V out over L, times 1 minus delta times Ts. So this provides us with the buck boost converter relationship, right?
This one
So
equal
this
to
V
this
out
one.
over Vn is equal to delta over 1 minus delta.
So this
If we
is
start to look at
voltage ratio.
instead of the
Duty cycle, 1 minus
you'll
duty
find
cycle.
that when the switch is
Take one sheet of the
across
assignment
this inductor,
Please take one sheet of the assignment 2.
It will be minus V out minus VC1, which is plus VC1, which is
So
V
this is
out
the
plus
voltage
Vn.
ratio.
So V out of the V out, we'll find that the voltage here also V input, and the slope will be V input over L. If you look at the
this slope equal to this slope.
you'll find that the voltage,
So we can obtain
which is
the relationship.
how much this is conducting, right? So it will be minus V out, and the slope will be also minus V out over L. So
This
the
is
current
VIL, this is minus V of L, this one equal to this
how
one.
much exactly same as the current level for the first inductor. So this will be the same level here. But the average, the value for the average will be different. So if you look at the average here for the inductor IL2, it will be the average of the current on the load, I out. But
The average
for the
is I
input inductor,
It is equal to V
IL1,
out
it will
divided
be
by R.
the input current.
This is
Depends
output
on
current.
the output resistance, but the ripple will be same and the slope will be same. Now let's draw the waveforms for the
Now,
current
see the waveform.
inside the inductor
The switch
and
and off.
capacitors. The capacitor again.
The switch and off,
as you see,
diode
the
and off.
switch is conducting or when the switch is on, so the current will be flowing in this direction
So,
or
this
I
way.
and also it will be
So
flowing in
switch
this
and off,
direction
this
for
way.
I.
And also this
Now,
way.
I agreed that the rate will be same for the IL1 and IL2, but the average will be different. Depends on the output load and input current. So in this case, because the on time is a little bit larger or greater than or longer than the off time, so we expect that this converter will be operating as a boost converter, and the input current definitely will be larger than the output current. So the average for IL1 will be higher, and if we try to draw, the current at this moment will be increasing for the
We have
IL2 or
here,
the
because this is show current charge.
will be less
In fact, current charge. So
when
if
it is off, we
this is
expect
IL1,
the current will be
IL2
in
is
this
like
direction
this.
and also in this direction at the same time.
So
and
when diode turn off,
inside
we
the
go this way,
will be released
and go this way.
will be something like this.
So
And
then
if you look at the
decrease.
current,
This
on
current
IL2,
also
it will be the
decrease.
same slope, but again, the average will be different. And these
So
two
this
slopes
also the
are-
same slope.
this slope and this slope are identical, and for this one, these two slopes also are identical. Now, also we said that the current inside this capacitor, it will be one time exactly same as the current that's coming from IL2, and when the switch is off, it will be the current that's coming from here, IL1. So let's draw these two currents. So when the switch is on, so the current will be how much? It will be IC1 will be minus IL2. This is IL2.
So
Here.
IC1 is here.
Minus
IL2
this
is here.
value.
IC1
And
equal to
when the
minus
switch is
IL2.
off, the current
So
will be
IL2 is here.
plus
Minus IL2
IL1.
is
So
here.
this is how the current inside this capacitor looks like. One portion coming from IL2 and the other
This
portion
is
coming from
IL2. This
IL1.
is minus IL2.
And now we know that V out over Vn for this choke converter is delta over
So this is
1 minus
voltage
delta,
ratio.
which means the output can be greater or smaller than the
Output can be larger than
depends on the
input
value
or less than
of the
input.
duty cycle.
Depends on
And
the
also the current I input over I output is also equal to delta over 1 minus delta, or
So
I out
if
over
we multiply by
1
these
minus
two,
delta over
it is equal
delta.
to 1
Because we
because
expect
power
that
is
for
equal.
ideal conditions,
Input
the
power
output
equal
power should be equal
output
to the
power.
input power. Now let's try to recall the ripple for the output. If you remember that this converter from the output
This is
just
low.
a buck converter.
This is
So
field.
this part
This
actually
is
is a buck
L2
converter,
inductor.
which is the
So
same
this is
as
buck.
the choke converter. So we can say that the ripple on the output here is exactly same as the ripple that is derived from the buck converter, which is 1 minus delta over 8 times the value of this inductor, L2, and this is the
This is
resistor
equal to
capacitor.
buck
So this is
converter.
L2, C2 times the switching frequency.
So this is the
How
result
to
of
find
buck
the ripple
converter.
on the first capacitor? We can simply integrate the current, we can say that delta VC1 is equal to 1 over C1 integration from delta TS to TS for the current, for the average current that is coming from IL1. Because if you look at the current in this C1, you'll find that this portion is coming
of the C1 capacitor.
L1. So we can integrate this value and find
this value
ripple on the
capacitor.
So this one from delta Ts to Ts. We can take the average for this value, no problems. So this will be how much? Delta VC1 will be 1 minus delta times Ts times IL1 over C1. If you want to make
this is the voltage variation across the C1 capacitor.
You'll find that the average value here is how much? IL1, and the time duration here 1 minus delta times Ts. So the area for the rectangle is how much? IL1 times 1 minus delta Ts, and this is the integration here, of course, over C1. So this is the ripple delta VC1 on the first capacitor or on the coupling capacitor. We don't like this current. This current actually is inside the converter, and we know that IL1 is equal to delta over 1 minus delta times IL2, and we know that IL2 here is equal to V out over R, so we can simply find the ripple with respect to the output voltage for this capacitor, the coupling capacitor. So if you just substitute these values here, you will find that delta VC1 for this capacitor is equal to how much? Delta 1 minus delta will go with 1 minus delta.
So now you try to
delta times V out
voltage
over C1
across the C1 capacitor.
And this is the ripple for the coupling capacitor. You'll find that we don't care much about the ripple here. If this ripple is large, there is no problems, as long as this capacitor transfers the energy from the input to the output. We care about the ripple usually on the input and the output side, because there we will find that the pulsating current, and we try to connect this converter with a smooth energy transition. But within the circuit, within the converter, there is no problems if this energy, if this ripple is large, that's fine. Coming back to the input and the output inductors, we said that the ripple on these inductors are same, and the slope for this one is equal to V input over L, and for this one is minus V output over L.
Minus V out divided by L.
We can find
this is increase.
These inductors. We can say that delta IL1 is equal to delta times V input over L1 times the switching frequency.
So this is delta IL1.
Repeat the same.
The current change.
Second inductor, which is delta
So please take one assignment here.
Input voltage
One
over
assignment.
L2 times the switching frequency. Now the maximum and the minimum ripple here is equal to how much? IL minimum is equal to IL1 minus delta IL over 2. And for the maximum, it will be IL1, for example, for the first inductor, plus delta IL1 over 2. And we agree that this is the IL, the average, and the current
is the average.
is delta
Average is here.
either 1
This is
or 2. Okay?
Current deviation.
Current here in this case is equal to IL1 minus delta IL2 minus delta IL over
IL1 minus
and
delta IL.
this must be
This is
kept
IL1
larger than
plus
0 to make sure
delta
that
IL.
we are operating
So this is this one.
for
This is
the
this one.
conductor for
And the
L1.
delta IL
We can say
is
for
the
input
deviation.
IL1 minus delta L1 over 2 must be larger than 0 to make sure that we are working in the continuous reduction mode. Let's try to find the value for IL1. So
the current always positive,
how much?
never reach to 0.
1 minus delta times IL2. And we know that IL2 average without the ripple that is going to this capacitor is equal to how much? V out over R. So IL1 is delta times V out over R times 1 minus delta. So we can say that delta V out over R times 1 minus delta minus delta Vn over 2 times L1 times the switching frequency. This must be larger than 0. And we can take this one and make it so this value must be larger than this value. That goes with delta. L1 must be larger than how much? V input over V output times R times 1 minus delta over 2 times the switching frequency. Vn over V out is equal to how much? 1 minus delta over delta. So we can say that 1 minus delta over delta here. So the value of the input inductor must be larger than 1 minus delta R over
keep the current continuous
times delta times the switching frequency. And this is the minimum value.
So this is the minimum value of L1. Otherwise, your current will be discontinuous.
You find the same for the second inductor for
so CCN.
Also,
continuous current mode.
Today we learned many things about the choke converter. There are many advantages for this choke converter.
So,
this converter has continuous input and
continuous mode.
The energy transition is very smooth.
Never reach
this transition or the current will be through the coupling capacitor. We know how to find the relation V out over Vn, I out over In. Also, we found the ripple on the output capacitor, which is exactly same as the buck converter. And also we found that the ripple for both inductors, the input and the output, the minimum inductance that keeps our converter in the continuous conduction mode. I hope that you enjoyed this lecture. If you have any questions, I'll be happy to hear from you.
So he explained very clear about choke converter, basic principle of the choke converter. Then we'll go to another video.
Hey everyone, welcome back to Power Electronics. I'm Tim, and today we're going to be talking about isolated converters.
So isolated converter.
I want to look at.
So now we discuss about isolated converter.
Where we kind of left off was here, right?
So isolated.
We came up with the idea of using transformers in DC to DC.
So we use transformer.
Having some DC source, converting that into an AC voltage, right? Which is kind of what switch mode power supplies do anyways, right? Considering the VX there's an AC component and a DC component. Right, so we have some DC to AC converters.
DC
right?
to AC.
Followed by our transformer.
Then we can use the transformer because this becomes
non-ideal transformer, which has leakage and magnetizer.
So this is transformer. The primary side. The secondary side.
And then we follow that with
then we have
an
rectifier.
AC to DC converter, right? Because the
AC to
transformer can really only
so rectifier.
transform AC voltages. Right?
So
and then our load follows that. So
DC
we
to
produce
AC,
DC voltage
then
on
AC to
divided by the
DC.
transformer, right? There's some dots, turns ratio.
So this is transformer. We want to use transformer. So we have to convert it to AC.
Choose some blocks to go in these areas, right? So I wanted to talk about this, kind of have a few options, and here we kind of have a few options. And I want to talk about buck-derived isolated DC to DC.
So this is buck converter, but we use a transformer. So we call it buck isolated DC-DC converter.
First, let's look at this. I'll call this part one, and I'll call this part two. So first, we're going to look at the inverter side, right? The DC to AC side.
So DC to AC.
DC to AC
this is
Even though
DC
inverter
to
has
AC inverter.
So, what do we got? Well, there are a few options. The two options I want to look at right now are the following. So, to convert a DC voltage into an AC
So
voltage.
now we want to convert DC to
component,
AC.
Right, we can do it normally with the buck.
But
right?
no DC component.
But we want to eliminate that DC component.
So
right?
we want to eliminate
so
DC
reminder for the
component.
buck.
So DC to
The
AC.
AC voltage, or the alternating voltage that we produce,
So,
is at the Vx node.
Alternating voltage.
Right, we can think about the switching cycle. And the AC voltage looks like
So
this. right?
AC voltage.
Goes from VG to 0.
Okay.
And of course, there is some duty ratio, right? So we want to do something similar, but eliminate this DC component, right? The DC component here is DVG.
So this
So,
is
what we
DC
do-
component.
Some topologies we can use is basically, just to remind you, this comes from,
So what topology can we use?
sorry, it comes from this kind of topology.
So we can use this topology.
This stuff. That's Vx.
So this topology.
This produces this waveform.
Then we
What
can
do is actually
generate
just
this
have
waveform.
use another copy of this. We can create another copy, and then that would produce our negative.
So then we can create
I'll show you that.
negative.
So, the first kind of AC converter we can produce, or the first kind of AC thing I want to talk about, DC to AC inverter, looks like this. So again, this is kind of just a redrawing of the conventional.
So this is DC to AC. So what
two
is
switches
DC
to the
to
left, right?
AC?
You can imagine that VG is over here.
So DC to AC.
Leg, whatever you want to call it. Right, so we have
So we have two
one
switch.
leg. And then to produce our AC voltage,
So we want to
just add
generate
another-
AC voltage. So we
right,
use
and then
H
you think, well,
bridge.
that's a that has
We
to
call
be
this
voltage.
is
That's a
H
positive
bridge.
voltage. How do we produce an AC voltage, right? How do we produce the negative voltage? And the trick really comes
So we use
by
1,
looking
3,
at
4,
the difference
4
between
switch.
these two voltages.
So
right? So we
we
have
can use
the voltage from this leg,
4
the
switch
voltage from
to
that leg,
generate
the voltage we
AC
look at is the
output.
difference between them. So we want to look at plus minus, I'll call this Vx. Right, this is the voltage we want to consider. And what does this Vx look like? I'll call it Vx prime. What does this Vx look like? Well, we have 4 switches.
4 switch.
So 1, 2, 3, 4. So there are kind of multiple states you can choose, but here we're only going to consider 3 states. So what are these 3 states? And why do we need 3 states? Well,
So 3 states.
it'll make sense when I draw that. So one state, I'll call it Q1,
Q1,
Q4.
Q4.
Right? This is one
These
state.
2 on.
Another state is Q2.
And then Q2,
on.
Q3.
And then finally
Positive,
is
negative.
a state we can choose is everything off.
So everything off.
And these are the 3 states we're going to use.
So we
Why?
have 3 states.
Well, if you remember, back to the buck, we kind of got this 0 voltage when we turn on this switch. However, if we turn on one of these switches, it just pulls one of these nodes to ground. And if we want the full thing to be 0 volts, there are a few ways of doing it. We could pull everything to ground, we could pull everything to VG, or we could leave everything off. Right? Those are kind of our 3 options. This is the option.
So
I'm
we
going to
have
choose,
3
but really,
options.
This is to produce 0 volts.
So this is 0
Right,
voltage.
so this
is
will produce
plus.
our positive voltage.
This is minus.
This will produce our negative voltage, and then we also need a 0 state, a state that
And
produces
this is
volts.
0
That's what we're going to
voltage.
choose everything off. There are other options. This is just what I'm going to show to demonstrate how this works. So these are the 3 states we have. And then what does this look like? What does the voltage we produce look like? Well, we can write it right here, right?
So
And
we
what we're going
use
to need
H
to
bridge
ensure
to
that there's
convert
equal positive
DC to AC.
and negative portion, right? If there isn't, then there's going to be some DC offset, right? Think back to the buck. So if we think back to the buck, because this is like always positive, there's always going to be a positive DC component to it. However, if there's an equal positive to a negative portion, then we're going to have zero DC offset, which means it's going to be completely AC signal. We want a completely AC signal because we don't want to saturate the core of the inductor of the
So
transformer.
we need AC.
Meaning, we want it to be symmetric about the x-axis.
So it should be symmetric.
What does that mean? Well, we want
Plus equal to minus.
we want to draw Vx prime of t, right? This thing, right? And we're going to consider two switching cycles, right?
So
And this
two
is
switching cycles.
to make the equations look nice. So we have two TS. That means somewhere over here we're going to have TS. And then this allows us to define the duty ratio in a way we're familiar with.
This is the duty ratio. Okay.
In the first portion of the switching cycle, we're going to provide a positive voltage.
So
right?
this one
Q1
is
and
positive.
Q4 are on. So Q1, Q4,
Q1,
right? These are going to conduct.
Q4.
So what does that look like? Well, Q1 is on. Then this top node is going to connect to VG. And
And
Q4 is
Q4
on. And
is
the
on.
bottom node is going to connect to
So it's
voltage,
on.
right? So
It's
that
on.
means that Vx
We
prime
can get
is
plus minus.
VG.
So it is positive plus
And
minus.
we're going to turn everything off, right? So all four switches are not going to conduct any.
So everything off.
Let's just go back. So again, Q1 and Q4 on means that we're going to have.
So we have positive
Then we're
here,
going to turn everything
Q1,
off.
Q4
There are
here.
multiple ways to have a zero state for this converter. I'm just
And
going
everything
to
off.
arbitrarily choose turning everything off.
Then
When
you go to
everything's off,
zero.
well, basically everything is floating. And if all else being equal, these two nodes should be at an equal voltage with some division between the capacitance of the switches. We'll just assume that it will go to zero. You
It
can
is
guarantee
zero.
it by turning on switches 3 and 4 or switches 1 and 2. Now this is just an example. So this is what we get for the first half, right? The first switching cycle, right? So this we're going to control with the duty ratio. So this is going to be DTS. So that's going to be DTS. And then we're going to do the same thing in the second half, right? Except here, for this first portion, right? Again, this is also going to be DTS. This line is going to be DTS. Q2 and Q3 are going to conduct. So
Now
when
Q2
Q2
and
conducts,
Q3. Q2 and Q3.
when Q2 conducts, well, that connects
Q2.
the bottom
Go here.
node to
So
the
this
right,
become
the
positive.
positive node.
This
It's
become
going to connect to
negative.
ground. Right, so
Positive,
basically we
negative.
invert the voltage, right? It's an inverter, so we invert the voltage and we get
So we
negative.
can get negative voltage.
And then again, we turn everything off.
So everything off becomes zero
So we
again.
have minus VG, that's on for DTS, and we have VG that's on for DTS. And all the other portions of time are zero. So this is the waveform we get, right? And it looks like the same as a buck converter, right? Except that we have equal positive and negative portions.
Equal
So this,
positive
the
and a
equal
negative.
positive
Equal positive
and negative
and a negative. So everything is zero.
ensures zero DC offset,
So DC value is zero.
which means we have a completely AC signal, which is exactly what we want for the transformer.
So we have AC
So this is one.
signal.
This is known as a full bridge.
We
Right?
call this is full bridge or H bridge.
Full bridge inverter, we could say, or
So
an H
full bridge
because
inverter.
it looks
Okay.
like an H, right? It kind of looks like an H.
Or we
So
call
this is
H
one
bridge.
you can have for the DC to AC converter. Another common
So we
option
can convert DC to AC.
looks like the following. So another option looks like this. So again, we have some VG.
So we have
And
VG.
connected again. So we still have this idea of using this buck kind of
So we
way
have two switch.
to produce an alternating voltage. But instead of using a secondary buck leg, all we do is have a capacitive divider, right?
Now we
So we
use
have
capacitor
C
here.
and C, they're the same capacitance. And again,
Same value of
look at the difference
capacitor.
between these two nodes. So
So-
ideally,
We can create AC
we'll call
output
this
here.
Vx, I guess that doesn't really work. I'll call it Vx star. So, all else being equal, the voltage Vg should divide equally between these two capacitances, right? It's a capacitive divider. That's kind of what we expect. In real life, it's a little bit more difficult, but because it's going to be loaded, it should work out okay. But what we expect is that we get
So
Vg over
each one share half.
this capacitor and Vg over 2 across this capacitor.
So Vg
So this node
capacitor.
is always
Each
at
one is
Vg over
half.
2. So we can imagine that this is always at Vg over 2.
Yeah, each one is half.
Now, this first stage, which we'll call switch 1 or Q1 and Q2, we're going to do something similar, right? So what we're going to do is, again, we have 3 states. So in one state, we're going to have Q1 on.
So Q1
And in another
on,
state, we're going to have Q2 on.
Q2 on,
Right? And then the third state, both off.
Q1, Q2 off. So 3
Right?
states.
And so this is going to be our 0 state again. And this is going to be our positive.
So this create positive, this create
So
negative,
again, what
this
does
create
the region
zero.
look like?
So
When we do
we have
this,
3 states.
So we're going to draw the x of t. Again, we want it to be symmetric around the x-axis. We're going to consider 2 switching cycles to complete. So I'll call this Ex star of t. We're going to consider 2 switching cycles.
So we have 2
Then we
switching
have
cycles.
our 1 switching cycle here. Again, we consider DTS because we still want to pulse width modulate
This
these
is
converters
Q2 cycle.
using the duty ratio to control that. Here we're going to have Q1 on.
Q1 on, positive.
Q1 is going to conduct here. Right? So if Q1 is on,
Q1 is
What does that
on,
mean?
we get
Q1 is
positive.
on, then we connect this positive terminal to VG. So this is at VG.
So this is
This at
VG,
over 2.
this
The
is
difference between
0.5
these 2
VG.
voltages is
So-
VG over 2.
From here to
Right,
here
so-
is 0.5 VG,
That means we're going to have VG over 2 here. So
VG over 2.
this half bridge,
We call this is half bridge.
this half bridge inverter,
Before it's
has
full
half the
bridge.
gain.
Now it's
Right? That's
half
kind of the
bridge.
bridge. You have 2 fewer switches.
Only
But
2
you have half.
switching.
Or really, the output voltage of this inverter is half, the amplitude is half that.
Half of the input.
Full bridge converter, full bridge converter. So again, here we have VG over 2.
So
and
0.5
then both
VG.
switches off. So both these are off and these are conducting. Basically, the circuit becomes incomplete, and then the voltage should equalize. So this should go to VG over 2. Again, a bit more complicated, but that is what happens. So it goes to 0. So if this node
So
is at
if
VG over 2,
both
then the
turn
difference
off,
between
then
the
this
positive
is
and minus-
0.
positive and negative is 0 volts, which means we have 0 volts here. And then again, in the second switching cycle, the second half of the switching cycle, whatever you want to say, over here, again, this length is DTS, and here Q2 is going to conduct, right? So if Q2 conducts, then we bring this node to ground. This goes to 0
Q2
volts.
conductor.
The difference between
This
positive and
become
negative is
zero.
now negative
This is
VG, right?
half
Or
VG.
negative VG.
So from here to here, minus
Right, and
half
again-
VG.
We go back to the 0 state by turning everything off. And this is the waveform we get. So again, it's symmetric about the x-axis.
So it is
There's the
symmetric.
AC component. And again, we can use this
So this one and this one is symmetric,
and have it
energy is
actually be converted, right?
0.
So we can use either one of these things. So this is like the first half.
So we can use half
So this
bridge
is one component.
or we can use full bridge.
Construct a bucket
Either one.
isolated converter. Next, we want to look at the rectifiers. And again, there are a few options for this, right? So one rectifier option, again, we can imagine here for the rectifier. So we have the output of or the secondary side of the transformer, right? You can imagine.
So
that.
this is the
Side of the transformer.
secondary.
One thing we can do
Before it's
is we
primary.
have a full
So
bridge
we
rectifier,
convert
right?
AC to
An
DC.
uncontrolled
So
rectifier.
first AC to
So
DC,
4 diodes.
then use transformer.
Right, so what do we
Then
do? We'll
AC
connect
to
one
DC.
terminal here, and we connect another terminal to the other side, right? And if we consider this voltage, I'll call it V secondary. And we follow this with basically a buck, right? So we have an inductor, a capacitor, and then our load, right? So again, this
So this is rectified.
is our load.
Full
So
bridge.
this-
rectified.
Output side,
So this is output side.
this looks like the output of a buck, right?
It is look like a buck converter.
Right, so it's going to act like a buck, depending on whatever this voltage is, which we'll call Vx. It's going to take the average of Vx basically, and that's going to be your output voltage. So what is Vx going to be? Well, Vx is clearly going to be related to V secondary, right? And how is it related? Well, let's label these.
So Vx is the DC value of the V secondary. Because
and we'll think about what happens when
rectified.
the secondary is positive and when it's negative. Coming back to the idea that this looks like a buck, what we can note
And
is that
this is a buck.
it's going to be less than whatever V secondary is, right? Because that's what a buck does, right? It steps down voltage. So if this is a buck,
So this is a buck converter.
then V out is going to be less than V secondary.
So
right?
V out is less than V secondary.
Of these voltages, right? So what does this mean? Well, we can kind of reimagine this whole section, right, this transformer section, as maybe being something like a voltage source that sits between these two terminals, right?
This is voltage source.
So V secondary is positive and larger than V out.
So this is larger than V out.
Then what's going to happen? Well, again, we have an inductor here, so
We have inductor
and the current should flow in one direction. Let's say this is a load.
and the current flow here.
Well, it's going to tend to forward bias D1 and D4.
So then D1 and D4 should be turned on.
Why is that? Well, consider this. There's a voltage here, V out, which is smaller than V secondary, right? So if V out is smaller than V secondary, then the voltage drop will be positive across
So
D1
voltage drop
and
here,
positive
voltage
across
drop
D3,
here.
but it'll be negative across D2 and D4.
So
and
this
D3,
always less than the
So,
amplitude
if
of
V sec is
the V
positive,
secondary. So
Then
if this is positive, this
V
turn
sec-
on, this turn on.
then it will tend to forward bias D1
So D1 is turned on, D4 is turned off.
D1 and D4. Conversely, if V sec is negative,
If V second is negative, then what happens?
it will forward bias D2
Then
and D3,
D2 and the D3
right? Meaning
automatically
that
turn on.
Vx
So
is going to
we
look
have
as
rectified.
well, right? So
If
really
this
what
is
we're trying to do
positive,
with Vx.
these two turn on.
What does a rectifier
If this
do?
is
It always
negative,
makes
these two turn
both
on.
positive and negative voltages always positive, right? That's what a full bridge rectifier.
So we
does.
call this is full bridge rectifier. Full bridge rectifier.
So, if V secondary looks like this,
So now we have V secondary. It is
we have-
AC voltage.
and remember, this V secondary comes from the primary voltage, which looks
So it is AC voltage,
as we described.
like this.
And again, it could be VG or VG over 2, depending on which converter we use. If this is V secondary, if we pass
So
it
this
through
is
a rectifier,
secondary voltage. Then we use
then it's going
full
to make the
bridge.
negative portions positive, and the positive portion positive, right? That's
So
what
what
we're-
is
so what we're gonna get is
rectified?
that
Change the negative into positive.
Vx of t. This is Ts, this is 2Ts.
So what is
It's
output?
going to look like this.
So we convert negative into positive.
Right?
So we
this
call
is
it
how
is
you-
rectified.
whatever you want. And this looks exactly like, or sorry, NVG. I'll just call it VSEC.
So we use the four diode to convert AC into DC.
This is also DTS. So again, this looks exactly like a buck converter.
So this is a buck
Instead of
converter.
G, we have this voltage VSEC. So this is one
So
of
this is
one
buck converter.
second kind of rectifier.
So when we turn on,
is
we got
called a
voltage.
rectifier.
when we turn off,
Which is slightly
we
different.
have 0 voltage.
Actually, one thing I didn't consider, or one thing I didn't say, is what happens when Vsec is 0?
So
Well,
what happens
that is actually the most interesting
when
part.
Vsec
So when
is
Vsec is
0? How about
there's
this
no
is 0?
difference between these two paths. And what will happen is
What
that
will
actually,
happen?
depending
If
on
this
the
is
different
zero.
voltages, we can say that all 4 diodes conduct.
Then
If
1, 2, 3, 4.
secondary is 0, then all 4
Turn off.
diodes conduct, and Vx goes to 0, right?
So Vx goes to 0.
It goes to 0 because basically there's a
Because
path
if this is
to ground, so
0,
the current
everything
will
is
move
0.
in this direction.
Output is
Right, so
0.
when Vsec is 0, all diodes conduct.
All diodes conduct.
Right, and actually what happens, like maybe ideally what happens,
So
is
1,
that
2,
the
3,
inductor
4
current splits
conduct.
evenly between these two branches, right? So maybe half IL will flow through D1, D3, and half IL will flow through D2, D4. IL over 2 through D1, D3,
So
and IL
each one share half current. So if 0 voltage, D1, D2,
That
D3,
is
D4
what-
all turn on.
tends to happen, right? So there's a kind of a special case when V secondary goes to 0, right? That's kind of cool. So this is one rectifier we have. Another rectifier
So this
is
is
the full
one
wave
choice.
rectifier. And this is a little bit different because it actually modifies what our transformer looks like. In fact, it adds another winding. And a full wave rectifier is simply adding another winding with the center tap, right? So you can imagine you can
So
stick a
we
wire
design
windings of
special transformer.
But the other way of thinking about it
Coil
is
series together.
the same turns ratio,
Okay. Different transformer.
right? Same dot directions. And what you
So
do
we have this one
is you
equal
add
to this
diodes,
one.
right?
And then we only use 2 diode.
Right, so,
We don't need 4 diode.
so this is like our positive node, similar for the buck.
So we call this
Right,
is
and
the
this
central
center
point
tap is kind of like
of the transformer.
the ground node of our output, right? So again, we have L, we have C, and we have the out over here.
So we have another choice. We design special transformer
again, if we
and then we
consider
only need
VS.
2 diode.
Finding V out is simply looking at the average of Vx. So V out is the average of Vx. So what is Vx in this case? Well, again, we have to consider
So plus, minus, then this turn off, this turn on. Plus, minus,
So-
plus, minus, this is a minus,
So we have
so
Vsec
turn
and
off.
Vsec prime. So if Vsec is positive,
So if positive, go this way,
I'll call this D1 and D2.
go this way.
If Vsec is positive, then what's going to happen?
D1
Well,
is turn on,
D1 is going to be forward biased, right?
so
And
D1
D2
turn on,
will be
D2 turn
reverse
off.
biased. And intuitively, you can think, right, we're applying a positive voltage
Positive
to
go
the
here,
to this side of the diode, which will tend to make current flow through that. Whereas for D2,
this
you're
turn
going to have
off.
a negative voltage, right,
Because
applied to
this
the
is
side of the
negative.
diode, which will tend to reverse bias it. If Vsec is negative, on the other hand,
On the other hand, this is negative,
well, again, this is
minus,
Vsec problem.
plus,
If it's negative,
minus,
then
plus,
D1 will be
this
reverse
turn
biased,
off, this turn on.
and D2 will be forward biased.
So D2 turn on, D1 turn off.
And again, you can intuitively think like we're applying a positive voltage to this side of D2,
And then go this way.
forward bias it. And then we're
So
applying
this
a
is
negative
minus,
negative
plus.
voltage
So
to
this
side
is
of
plus,
D1,
minus.
we'll reverse bias it.
And then this turn off.
again, the question is, if Vsec is 0, then what's going to happen? Well, if Vsec is 0, then basically
This one is
this is
zero.
a short. This whole thing is a short.
Short
There's
circuit.
0 volts across this winding, there's 0 volts across this winding.
This 0,
Which
this
puts
0.
D1 and D2 in parallel. and effectively splits the current between them.
So each one share half current because 0, 0.
Right? So we kind of have three states again. One state D1 conducts, another state D2 conducts, and the third state, both of them conduct. And that kind of matches up with the way we're controlling the primary side, right? We have three states typically with the primary side. One state there's a positive voltage, one state there's a negative voltage, and one state there's a zero voltage. So the zero voltage state is really very important in understanding how this works because it creates this synchronous rectification
This is synchronous
right? Where we provide 0 volts to the out and allow control over the output voltage, right? The length of time that we have a positive voltage compared to the length of time that we have 0 voltage actually is what controls Vout, right? If there was always a positive voltage at Vx, if it never went to 0, then Vout could only be related to V secondary. But because there's like some period of time when it's on and some period of time when it's 0, then the average can be decreased and therefore controls through pulse width modulation. So these are kind of our two options. So what happens if we stick these in, right? Right? We can freely kind of stick either inverter into the first slot and either rectifier into the second slot. So what happens, what do we do? So arbitrarily I'm going to choose the full bridge rectifier on the primary side, and the full full bridge inverter on the primary side, and the full wave rectifier on the secondary side. And what do we get? Well, we get this Buck-derived topology, a full bridge, you could say.
We have 4 bridge here. This is the primary side. So we have 4 bridge.
Our positive and negative, which will connect to our transformer.
So
And
this
positive
is
and
H
negative
bridge.
very important because it's what allows us to, in a sense, relax the magnetizing inductance, right? We apply positive voltage, kind of charges up the core, and then we apply negative voltage, which relaxes the core, discharges the core, ensuring that our magnetizing current never goes above saturation, which ensures that we can couple the primary side with the secondary side. So we connect this to our transformer,
So now we have
right? So we have a
transformer.
non-ideal transformer with the
We
magnetizing inductance.
H bridge here. We have transformer here.
Which is then connected to, and here I'm going to choose 1 on the primary side and N on the secondary side.
So this is a 10 ratio.
Wave
The
rectifier with
transformer.
that center tapped core, right? So again, this is to N. So they're the same turns ratio.
So
And
how this
connect
is central
both of
pole.
these
Then we use 2 dial.
to an inductor. So we have an inductor over here,
So we have inductor, capacitor.
followed by our load, right?
Yeah.
And again, we could choose either one for this.
Okay. So it
Full
is
bridge,
spatial
full bridge,
transformer.
full bridge or half bridge inverter. But choosing this specific combination, this is what we get. So we have Q1, Q2,
Q1, Q2, Q3,
Q3,
Q4.
Q4, L
We have
equals,
H bridge.
and you could include a leakage on the secondary side, right? So we could have
So we use
L equals,
DC
and we
to
have
AC
L
and
leakage,
AC to
and we
DC.
have L magnetizing, and we have finally our output inductor L, C, and V out is.
This is field.
Just slide over a little bit. So V out is here, and there's with our load.
This
Again,
is
you
low.
can consider Vx here. And this is kind of everything. So how does this work? Well, to understand how it works, we have to draw the waveforms. And there are a few waveforms to draw. So I'm going to ignore drawing like the leakage inductances for now, because really the magnetizing inductance is what matters most for this, and the output inductor. So again, we have 3 states. And the 3 states on the primary side align exactly with the 3 states on the secondary side. So 3 states. And the 3 states are
So 3 state.
Q1,
Q1, and Q4.
Q4 are conducting on the primary side, and D1, right? So we're going to
Then
apply
plus, minus, then D1 turn on.
D1 conducts.
So Q1, Q4, and the D1 turn on.
Then we have Q2, Q3 on the primary side.
Q3, then this become negative,
D2 conducts.
and D2 turn on.
And then finally, we say nothing, open
Nothing.
circuit,
So
or 0.
all of them open circuit.
Nothing on the primary side.
Yeah.
And
Every
D1
switch
and
turn off. Then they share the same current, D1, D2 turn on.
Right? That is how this thing works. So let's draw some waveforms.
So now he try to draw the
We
waveform.
have on the primary side. So I'm going to draw, how do we usually do this? Well, we draw the voltage across the inductors and the current through the inductors. So first I'm going to draw V1, which is again the magnetizing inductance voltage. So
This
this
is
is T1 forms what the
turn on.
magnetizing
So
current will
positive.
be. This is T2TS, TS. So again, we have our 3 states.
Okay.
that
3
have 4
states.
slots. So this is like state 1, state 2, state 3, state 2. Right? So over here, we're going to apply VG.
So Q1,
And it
Q4.
goes to 0.
So positive.
Right? Nothing's conducting.
Then
Then it goes to
0.
minus VG. And it
Then
goes back
Q2,
up
Q3, negative. Then
to 0.
all
right?
of
So
them
minus VG.
turn off.
VG.
So here.
This is V1.
So this equal to this.
Label what V1 is. So we have this is V1, and then you can say this is V2, and you could say this is V3. They're related to each other because they have the same turns ratio. So that's V1.
So V1
From
is
this,
here
we can draw the
Plus.
magnetizing current.
minus. This is magnetization.
So again, this
voltage.
is actually DTS, and this is also DTS. So the magnetizing current.
So this
So here,
magnetization
which
current.
means we're ramping up
So
with
increase
G
because
over L,
positive voltage increase.
right? We reach some
Then
some
become
current,
zero, no
whatever it
change.
is, and then here we discharge with the same amount. So this
And
is
then
minus VG,
negative.
back,
Then return to zero.
right, and it goes back down to 0.
So
as long as
begin from
this P
zero,
current is less than
return to
saturation
zero.
current, then we're good. So in a sense, this determines the minimum frequency we can have, right? If we switch too slow, then this current can get too high. So the size of the transformer kind of determines how fast you have to switch. The larger the transformer, the more core flux it can sustain, which means the slower you can switch, basically. And the smaller it is, well, the faster you're going to have to switch to ensure that it doesn't saturate. So this is a magnetizing current. Again, we have the
Oh,
primary
this is
voltage. on one side,
magnetization
Now we can draw the
current.
secondary voltage. And the secondary voltage,
So this is primary current,
or V2,
primary voltage. Now he try to
is
draw
really just
secondary voltage.
of the primary voltage, right? We have TS, 2PS, DTS, right? So in the first half, well, we apply VG,
So now
and we assume
secondary.
that we're coupling the primary to the secondary side. So V2 and V3 are going to be the same.
V2 and V3.
Right, there it is, V2 and V3. So it's going to look like V1 except multiplied by.
So V1, V4
N, right?
plus minus,
So
plus
V2
minus,
and
plus
V3
minus.
as follows.
So it is plus.
NVG followed by
So
0.
NVG because 10 ratio. And then 0, here
Right,
0.
so we stepped
This
up the
is
voltage,
negative.
or
This is
transformed the
negative.
voltage by our turns
But
ratio.
the voltage from primary to secondary
Then this
have
goes through
the 10 ratio N.
the full wave rectifier, right?
So after
As
rectifier,
we described,
all become
to
positive.
force this positive and negative voltage
So,
to become
Negative become positive.
So if we draw the
After
Vx
rectifier.
voltage, it's going to look like this, but all the negative parts are going to be positive. So Vx is going to look like NVG,
So this is NVG, this is 0.
NVG, and
This
0.
is minus
And 0
NVG, but
so this is how we
become
chose
plus
TCS instead of
NVG
Yes.
because rectifier.
So that at the output voltage looks nice. So this is again DTS, this is 2TS.
So this is
Cool.
output
This is Vx.
voltage.
And we know that because this is a buck, the output looks like a buck, it's just an inductor and a capacitor. We could apply IVSB to L, but because we know that we're just averaging Vx, then we know that the output voltage, or really, we can draw the,
So what is the output
okay,
voltage?
we'll draw the inductor voltage just to be fully complete.
So what is inductor voltage?
So this is T, this is going to be VL of T.
So VL, the secondary inductor.
This is 2TS, this is TS, DTS. So what is the voltage across the inductor? Well, pretty simply, it's going to be Vx minus Vout. Again, we're assuming that Vout is going to be constant, it's a constant voltage. We expect this to be a DC to DC converter. So simply, we just subtract off Vout. It's going to be some amount. I'll just draw it arbitrarily here.
So VL.
NVG minus Vout over here, down to minus Vout. And then again, NVG
NVG.
minus Vout,
This is
down to
minus
minus Vout.
VO. And then this
Right,
area
so,
should be
in a
equal
sense,
to this
You
area.
can think about the IVSB directly from this, but what I'll do now is draw the inductor current.
So how about inductor current? The secondary inductor current.
So we're
We
doing the same
have
thing we
positive
did in
voltage.
the first half. We charge up the inductor.
So we charge.
There's some average current flowing through it, which is Vout over R load. Here we charge the inductor up with
charge.
minus VG over Vout over L.
NVG minus
And
VO
we discharge
divided
it
by
with the
L.
minus Vout over L.
This is minus VOL.
Again, we charge it
It
up
will
again.
become negative.
And we
So
discharge. Exact same
positive,
thing. We
negative.
have some average current. IL is equal to Vout over R load.
So this is average. Average is VO.
And you could do the output voltage. The output voltage is going to look exactly like a buck. But really what I want to do now is think about what the average output voltage actually is. So Vout is going to be
What is the output
basically
voltage?
the average of Vx. And again, this is like a really simplified way of
So
doing it.
output voltage is
We could do IVSB,
Vx
so VL,
average.
the average of VL over one switching cycle is equal to 0. Look at the VL over here. If think about one switching cycle, it's going to be D times NVG minus Vout.
So this one
Plus
multiplied by duty
times minus Vout.
plus this one
Which
multiplied
means Vout is going to be T times NVG. Right? In
T
other
times
words,
VG.
for this isolated Buck-derived topology, we get to the conversion ratio, M of D.
So
is
what
actually
is
also
the voltage ratio?
And it's equal to N times D.
So if
Right,
you
so
have 10 ratio, you have to consider 10
Step
ratio.
up the voltage.
So
by
10 ratio
changing
multiplied by
the
duty
right?
cycle.
So say N is 100, then we can increase the input voltage by a factor of 100 and then step it down depending on.
So
the
this is always less
Right,
than
that
what,
is
but
very
this
possible.
could be
So by
very
using
large.
transformers, we can actually get buck converters to step up voltages, right? And sometimes that's useful. We can also get it to really step down voltages. So we could choose N
So
to
we
be
can choose
small,
N.
1001. We could turn a 100 volt input voltage down to like less than 1 volt. That's totally possible.
So we
And
can
that's kind of the
increase
extra power, right? So this
the
is like
the
extra
ratio.
gain.
We can change the ratio.
We don't have to rely on duty ratio to control how
So now
big
it
the
is
voltage
not
is.
only
Now
related
that's
to
extra
duty
variable.
ratio, but also
Admittedly,
related
you have
to
to
the,
decide what
N
to
ratio.
play, but you can control it with N, right? You can choose.
We
You
can
want
choose
it
N.
to be 1,000 or 20 or whatever number you want.
Then we
And
can
again, you
change
can fit in
the voltage
half
ratio.
bridge. On the input side, we could fit in a full bridge rectifier on the output side. And it would be a little bit different, but it would look pretty much the same, right? So if you use a half bridge, you just have to have a factor of 1/2 added to this because the input voltage is basically divided by 2. But other than that, it's pretty much the same. So that's it for now, just explaining the converter. Eventually we'll go in depth and like do a design thing with an isolated converter, but for now, that's it for this Buck-derived topology. We'll talk about other types of isolated converters later. Thanks.
So we will have 20 minutes break. So
Hey everyone,
we
welcome
will
back to
start
Electronics.
with
Today, we're looking at insulated DC
1040.
converters again.
So we have 20 minutes break.
是有的会到倍加其实。 we have call.